Hello everyone, welcome. For this problem, our goal is to find the partial fraction decomposition for the following expression: x squared plus x minus 1 over the quantity x plus 1 times x minus 1 times x minus 2. There are two ways we're going to approach this problem. The first way is called the method of undetermined coefficients, which is the standard way most textbooks use for determining partial fraction decomposition of expressions. The second way is known as the cover-up method, which is significantly easier as long as the rule is applied correctly, which we'll see towards the end of the video. The first step is to determine the correct form of the partial fractions needed to decompose our expression. You can usually find a table of partial fraction forms in your textbook or some online resource. I've provided one here, and we see that the partial fraction decomposition form that applies to our particular expression is the third row, which we can set equal to our expression. Substituting values in for lowercase a, b, and c, we end up with the following equation, where a, b, and c are unknown constants. Next, we can move the entire denominator over to the right-hand side and cancel out common factors for each term. Next, we can multiply out every product on the right-hand side, and we end up with the following. Next, we can distribute the unknown constants a, b, and c in each term, and we see that we end up with three types of terms: terms containing the factor x squared, terms containing the factor x, and terms that are just constants. We can collect like terms and pull out common x factors as such. We see now that we can match the coefficients on the right-hand side with the corresponding coefficients on the left-hand side. Equating the coefficients in front of the x squared term, we end up with the following equation. And equating the x coefficients results in the following equation. We can do the same with the constants, ending up with the third equation. We now see that we have a system of three equations with three unknowns. We can solve this using any method. I used the second equation to write b in terms of a, and then substituted this into the remaining equations to determine the values of a and c. We can then add the two equations together to determine the value of a, and we end up with a is equal to negative 1/6. Using the second equation, we can determine b, and we end up with b is equal to negative 1/2. We can now use any one of the equations containing c to determine c, and we end up with c is equal to 5/3. At this point, we have completed the partial fraction decomposition using the method of undetermined coefficients. However, there's an alternate way to arrive at the solution, so let us reset and approach the problem from the start. We can set aside the values of a, b, and c just to remind ourselves that these are the answers we'd like to obtain at the end of the problem. The first step in the alternate method is to focus on any one of the coefficients we'd like to solve for. Let's focus on the coefficient a. If we'd like to solve for a, we need to pay attention to all occurrences of the denominator of the quotient that contains a, which is x plus 1. What we're going to do is we're going to move over only the x plus 1 to the right-hand side as such. This is in contrast to the method of undetermined coefficients we discussed previously, which requires us to move the entire denominator from the left-hand side over to the right-hand side. We can cancel out the common factor in the term containing a, and we end up with the following. Now, we want to pay special attention to these x's. These x's are advantageous since certain values of x results in both of these factors becoming 0, which is useful to us since it causes the unknowns b and c to disappear. If we'd like these terms to disappear, we could simply plug in the number negative 1 in for x. Let's not forget, we have to do this for all x's in our equation, so all occurrences of x need to be negative 1. This is advantageous since it results in both terms containing the unknowns b and c to go to 0, and the unknown a is simply equal to whatever's left on the left-hand side of the equation, which after computing is negative 1/6, which is the same result as before when we used the method of undetermined coefficients. We can now repeat this process for the next unknown coefficient b, and now we want to focus on the denominator of the term containing b, x minus 1. We can move this over to the right-hand side, and after simplifying, we end up with the following. Now, let us focus on these x's and pick a value for x that would result in the terms containing the x's to vanish. We can choose x to be 1, which forces all terms other than b to be 0, and so we end up with the following. After this is done, b is simply equal to the left-hand side, which after computing is simply -1/2, which is exactly the same result we've obtained when we use the method of undetermined coefficients. Next, we could focus on the final unknown coefficient c and take note of the denominator x minus 2. What's convenient about this method is that once we know what's going on behind the scenes, we don't have to write out the step where we multiplied the denominator under c over to the right-hand side every single time. We could simply plug in the value for x that results in the factor x minus 2 to be 0, and we already know how this would cause the a and b terms to vanish on the right-hand side. We can select x to be 2, and then we could simply imagine that we cover up the x minus 2 factor on the left-hand side, and then compute what remains, which results in the value of c, which is simply 5/3, which is the same result as before when we used the method of undetermined coefficients. This brings us to our final answer, which after plugging in values for a, b, and c is the following. Now let's move on to a case where the procedure we just described doesn't work as planned. Let's focus on the expression 1 over the quantity x plus 2 squared times x plus 1. Referring to our table of partial fraction decompositions, we see that the fourth row corresponds to the case we are dealing with. After making the appropriate substitutions, we end up with the following on the right-hand side, where again a, b, and c are unknown constants. Let us now proceed with using the cover-up method to determine the unknown constants. Let's start with finding the value of c, where the expression under c is x plus 1. Again, our goal is to turn the x plus 1 expression into 0. We can do this easily by substituting -1 in for x. We can then simply cover up the denominator of the c term and compute the result, ending up with c equals 1. We can now move on to the term containing b with the denominator of x plus 2 squared. We can easily turn this into 0 by substituting in -2 for x. We can then cover up the denominator of the b term and compute the resulting expression, resulting in b equals -1. We now move on to the last term containing a, the denominator of which is x plus 2. What's important to point out here is that there is no standalone x plus 2 factor on the left-hand side. There is a x plus 2 squared factor, but remember, we already used this factor to determine b. Despite this, it's possible you may be tempted to just move one of the x plus 2 factors over to the right-hand side and proceed with the process, which after simplifying results in the following. Now, there's a bit of an issue here since we have divided out the factor that we would otherwise use to cause the b term to go to 0. There is nothing multiplying b that we could use to our advantage for eliminating b by choosing a strategic value for x. If we were to continue with the process and select x to be -2 in the interest of making the term containing c to vanish, we would end up dividing by 0, which results in a being expressed in terms of undefined quantities. So what do we do when this happens? Well, we actually don't have to use the cover-up rule for the final unknown a. The reason is we already know the values of b and c, and we could simply just plug those in and pick any value of x so long as the quantities remain defined, and then solve for the unknown a. We could simply select x to be 0, and after simplifying and solving for a, we end up with a is equal to -1, which results in the following final answer.